আমরা সেমিকন্ডাক্টরটা পড়ছিলাম লাস্ট দিন। আমরা হচ্ছে পিএন জাংশন শুরু করে দিয়েছি।
হ্যাঁ,
তোমার কোনো যদি কোয়েরিজ থাকে, কোয়েশ্চেন্স থাকে করতে পারো।
না ওই থিওরি রিলেটেড সেরকম নেই, প্রবলেম করছি এখনো।
আচ্ছা, তাহলে সেমিকন্ডাক্টরে মেইনলি দুই ধরনের চার্জ ক্যারিয়ার থাকছে, একটা ইলেকট্রন, একটা হোলস। যে সমস্ত সেমিকন্ডাক্টরে, এক্সট্রিনসিক সেমিকন্ডাক্টরে আমার ইলেকট্রনসটা মেজরিটি চার্জ ক্যারিয়ার, মানে ইলেকট্রনের ডেনসিটি বেশি, তখন তাদেরকে আমরা বলছি কি এন টাইপ সেমিকন্ডাক্টর। আর যে সমস্ত সেমিকন্ডাক্টরে হোলসের মেজরিটি বেশি, তাদেরকে আমরা বলছি পি টাইপ সেমিকন্ডাক্টর। সরি, I should continue in English. So we have learned about N-type and P-type semiconductor. Also, we have started our discussion on PN junction. We have learned about the mechanism of conductivity, diffusion, and drift. And we have learned about barrier potential, depletion region, and barrier field. Up to that, we have discussed. Now, today is 16th. The circuit symbol of PN junction. It is something like this. This is P side, this is N side. Okay, so you can say this is anode side and this is cathode side. So this is the circuit symbol of a PN junction. Let us find how PN junction works. Now we can connect the PN junction in circuit in two type connections. One is called forward biasing. In forward biasing, P terminal connected to the positive terminal of the battery and N terminal connected with the negative end of the battery. Okay, so when we connect this PN junction in forward biasing, this is P side, this is a before connection, this is the depletion region. Now it is connected in this way. Now, what is the direction of the barrier potential? It is N to P. So this is directed in this direction. This is VB. And this potential is directed in opposite direction. So the applied potential is in opposite of the barrier potential. Applied potential V, this is V, is in opposite of the barrier potential. So what will happen? The barrier height will reduce. So initially say this is the barrier height. So initially the barrier height was this VB. Due to connection, the barrier height has reduced. So there is a change in the barrier height. How much? This is the applied potential. So now the barrier height, or not only this, sorry, this is the height of the barrier, and it will be VB minus V. Okay. So the barrier, sorry, these dotted lines are the initial positions of the bands before connections. This is in N side, this is in P side, this is P side, this is N side. But after connection, with the P side with the positive terminal of the battery and N side with the negative terminal of the battery, there is a reduction in the barrier potential. Why the reduction? Because the applied potential is in opposite direction of the barrier potential. So it will effectively, there is a reduction of the barrier potential. So the effective barrier potential decreases. How much? VB minus V. So what will happen? The energy barrier across the junction decreases. This is the Q into VB minus. Initially the energy height was Q into VB. Now it is Q into VB minus V. So energy barrier
into VB minus V or VA minus VB?
VB minus V. Initially it will be VB minus V. When this V goes over VB, then it will be V minus V. Is it understandable?
Yes, sir.
V is the applied potential. And VB is the barrier potential. So when you connect the diode in forward biasing, that means the P terminal connected to the positive end of the battery and the N terminal connected to the negative end of the battery, then there will be the applied potential and the barrier potential are in opposite direction. So there will be reduction of the barrier potential, and hence barrier energy will also reduce across the junction. So what will happen? Due to reduction of this barrier potential, the majority charge carrier, that means holes from P side and electrons from N side, begins to flow towards the junction. Electrons from N side begin to flow so electrons and holes now start moving towards the junction. The diffusion of electrons and holes into the depletion layer decreases the speed. So what will happen? The width of the depletion region will decrease due to, initially it was the width, now it has decreased. So due to motion of these charge carriers, the diffusion of electrons and holes into depletion region decreases the width of the depletion region. Okay, so what will happen? The effective resistance at the p-n junction will decrease. So when we connect the p-n junction in forward biasing, the depletion region will decrease, the barrier height will decrease, the depletion region will decrease, and that is why the effective resistance across the p-n junction will also decrease. The circuit symbol I will show here, how the circuit will look like, how the circuit we will draw. It is something like this. There will be a key, capping key, a resistance which is known as safety resistance, and there will be a milliammeter. And you can also measure the voltage with a voltmeter across the p-n junction. Okay. Now, the second type of biasing, what I have mentioned, is the reverse biasing. So what do you expect in case of reverse biasing? Here, the N side is connected with the positive terminal of the battery, and the P side is connected with the negative terminal of the battery. So now see, both the barrier potential VB and the applied potential V are in same direction. Both the barrier potential and the applied potential are in same direction. So what will happen? The barrier height will increase. It was the initial barrier height. Say this is Q into VB. Now the height has been increased. Now the barrier height has been increased, and the new barrier height will be Q into VB plus V. It is understandable. Is it understandable?
Yes, sir.
Yeah. So in case of reverse biasing, the width of the depletion region will increase also. Okay. So initially the width was something like this. Initially the width was this. Now finally it has increased to this. So this is the final width. The dotted line showing the initial width of the barrier potential. So what will happen? Barrier potential increases to VB plus V. Majority charge carriers moves away from the junction. So increase in the width of depletion region, barrier energy increases, to Q into VB plus V, and resistance across the PN junction also increases, and effectively no current flows across the junction due to majority charge carrier. No, there is a feeble minority current. We are not going to taking account of that. Effectively, the current will become zero. No current will flow across the junction due to majority carriers. So you can understand the current will flow when it is connected to forward biasing, and there will be no current when it is connected in reverse biasing. And the circuit symbol, I will show here. The circuit symbol looks like something like this. There is a milliammeter, and you can measure the voltage with a voltmeter. Okay, these are safety resistance R. Okay. Now, the most important is the characteristics of this PN junction diode. Characteristics means the relationship of current and voltage. So it is known as VI characteristics. First, with forward biasing, which is known as forward characteristics. Forward bias characteristics. To draw the forward bias characteristics, we will use the circuit like this. Here we will use a variable source. So we can vary the voltage. Okay. And we will measure the current through this milliammeter and the voltage across the diode with this voltmeter. And it will shown like initially there will be no current. Why? Because to have some current across the junction, your voltage should be more than the barrier potential. So here V in volts and current in milliampere. So it looks like this. And as it crosses the cutoff region, cut-in region. This is called cut-in voltage. So when this V is equals to VB, up to that, you will get no current. But after that, the current will increase sharply with very little increase in the voltage. So you will get very large current with very little change in the voltage when you go above this cut-in voltage. Okay. So it is not a straight line graph. So do not obey Ohm's law. Initially, the current increases very slowly, almost negligibly, till the voltage across the diode crosses a certain voltage, which is called the threshold voltage or the cut-in voltage. Okay. So up to the threshold voltage or cut-in voltage, increase in the current is very low. Okay. But in generally threshold voltage for silicon is about 0.7 volt. For germanium is about 0.2 volt. Okay. So before this characteristics voltage, the depletion layer plays a dominant role in controlling the motion of the charge carrier. So this region is basically depletion region dominated. Okay, that is called space charge dominated region. Before threshold voltage, current is negligible. This is known as space charge dominated region. Now, after the cut-in voltage or after the threshold voltage, current increases sharply with very little increase in voltage. Here the majority charge carrier feels negligible resistance at the junction. Okay. Majority charge carriers feels negligible resistance across the junction. The width of the depletion layer becomes zero. There will be no depletion region when the current flows start flowing largely. Okay. So this is the forward characteristics of a PN junction diode. And there is another characteristics which is called reverse characteristics. Is it understandable?
Yeah.
Is it understandable?
Yeah. Yes, sir.
If you have any questions at any point, you may ask. No problem. Okay. Just ask it.
Yes.
Because these things are quite new and to you, so you may feel some problem, some difficulty in understanding. So please feel free and ask question. Secondly, that is called reverse bias characteristics. For that, we will take similar type of circuit. Here also, this battery or source is variable source. Now, if I draw the characteristics, here voltage is negative. V, this is reverse bias voltage in volts, and current in microampere. So here we have to use a microammeter, and the characteristics is something like this. There is a breakdown after certain voltage. This voltage is called breakdown voltage. So when the diode is in reverse bias, the reverse bias voltage produces a very small current. So that is the due to minority charge carrier, flow of minority charge carrier. Reverse bias voltage produces very small current due to the flow of minority carriers. Here minority carriers or majority carriers means majority charge carrier and minority charge carrier. It is of the order of microampere, and the current of the order of microampere, the current remains almost constant up to a certain voltage called breakdown voltage. So up to breakdown voltage, current remains very small. Okay. This small current is known as reverse saturation current, and it is due to flow of minority carriers across the junction. Now, when the reverse voltage across the PN junction reaches a sufficiently high value, the reverse current suddenly increases to a large value. When the reverse voltage reaches a sufficiently high value, obviously in a negative direction, the reverse current suddenly increases to a large value. This voltage at which breakdown of the junction diode occurs is called breakdown voltage or Zener breakdown voltage. The voltage at which this breakdown occurs is known as Zener breakdown voltage or peak inverse voltage. So when you go in the higher classes, if you study with physics, you will learn that there are two types of breakdown basically. One is general breakdown, which is somewhat controlled. Another breakdown is there, which is called avalanche breakdown. We are not going into details of that in this level. So this general breakdown voltage is ranges in the range 1 to 2 volt. To several hundred volts. So this range is quite high, and it depends on the dopant density and the depletion region. So if we take both the characteristics together, then we have to scale it properly. Here current is in milliampere, here current is in microampere. So this will be something like this. In reverse direction, this is something like this. So this is V in volts, V in volts. This is forward biasing voltage, this is reverse biasing voltage. So this is a complete characteristics of a PN junction diode. Now, the resistance of the PN junction diode is known as dynamic resistance. Why it is dynamic? Because at different point, resistance is different. So it is changing dynamically. So it is called dynamic resistance. Dynamic resistance, RD. It is delta V by delta I. So if you take here very small change in voltage, very small change in current. Okay, so it is measured in ohm. So this is called dynamic resistance. Why it is called dynamic? Because at different portion of the characteristic curve, the resistance will be different. Now we can use this junction diode as a rectifier. Now what is rectifier? Do you have any idea?
Rectifier is a tool.
Hmm?
Rectifier is a tool, kind of.
Mhm.
But what is the purpose? I don't know. What is the main purpose? I don't know actually.
Okay, no problem. So basically rectifier is a process. The process, rectification is a process. The process of converting alternating current into direct current is called rectification. And the device used for this process, the device is called rectifier. Now junction diode can be used as rectifier. Why? Because you can understand that in junction diode allow flow of current in forward biasing condition, but restrict the flow of current in reverse biasing condition. So it can be used as a rectifier. Now there are mainly three types of rectifier. One is called two types of rectifier. One is called half wave rectifier, other is called full wave rectifier. Now this full wave rectifier is of two kinds. One is center tap type, other is bridge type. We will discuss this rectification process by simple diagrams. First, we will consider half wave rectifier. In half wave rectifier, we use only a single PN junction diode. We use a transformer which is connected to the AC source. This is the primary of the transformer. This is the secondary of the transformer. Now here we will connect one diode, and here the load resistance. RL. This is diode D. Now, during the first half cycle, this is say my input AC. Say AC voltage in volt, and here we will measure the output. Now, what is happening during the first half cycle? This terminal, upper terminal of the transformer, say positive, and the lower terminal is negative. So the diode is connected to the positive terminal. P end of the diode is connected to the positive terminal. So current will flow, and it will flow through the load resistance. So there will be a voltage drop. Okay. But in the second half cycle, when the lower terminal is positive and the upper terminal is negative in this half cycle, then what will happen? The P side is connected to the negative terminal and the N side is connected to the positive terminal. So no current will flow. In the next half cycle, when again the upper side is positive and the lower side is negative, current will flow. So you will get a voltage drop. But in the next half cycle, there will be no current, so no voltage drop. So here you can see why it is called half wave, because only the half of the wave is rectified and the other half is blocked. Only the half of the wave is rectified and the other half is completely blocked. Okay. So that is why it is called half wave rectifier. Is it understandable?
Okay.
Okay. Next is full wave rectifier, center tap type full wave rectifier. Now you can understand what is the problem. You are losing half of the wave. You are not getting the energy of this half of the wave. So only the half of the wave is rectified, and it is not smooth also. There is a huge change in the value of the voltage. Up to this, in this middle, there is a zero voltage, then there is a peak, then there is a zero voltage, then there is a peak. So the obtained DC is very much unstable. Okay, that is why we will use this center tap type full wave rectifier. So here we will use two diodes and we will make a tap at the center of the transformer. That is why it is called center tap type. This is the primary of the transformer. This is the secondary. Now we will use two diodes G1 and diodes G2. There is a load resistance RL, which is connected with the center of the transformer. Okay, this is RL. Now see what is happening. This is the input. And here we will measure the output. So this is my input AC, and here I will plot the output. So say during the positive half cycle, first half cycle, this upper end is positive, the lower end is negative. So what will happen? Diode D1, the P end of the diode D1 is connected to positive terminal, but the P end of diode D2 is connected to negative terminal. So D1 will conduct and current will flow through the load resistance, and you will get a voltage in the output. Now during the next half cycle, this lower range is positive, upper range is negative. So D1 will become blocked and D2 will connect. Current will flow through D2 now. But in the load resistance, you can see the current will flow in same direction. So you will get like this, this. So here both the half has been rectified. In previous case, the lower half has been blocked only, but here the lower half has been converted into opposite direction. So this is called full wave rectification. So here the fluctuation is there, but the fluctuation is low than the half wave rectifier. And here you are getting much more energy. But still there is a problem, as you are using the tapping at the center. So you are utilizing only half power of the transformer. You are utilizing only half power of the transformer. To overcome this difficulty, another type of, so this connection is also okay, na? Okay. To overcome this problem, we have another type of rectifier, which is called bridge type full wave rectifier. Here we will use 4 diodes, 4 PN junction diodes. These are arranged in the form of a Wheatstone bridge. This is my transformer. This is primary, this is secondary. And here we will connect the load resistance. So you can see here I am utilizing the whole transformer. So during the first positive cycle, so this is my input voltage. So during the first half cycle, say the upper portion is positive, the current will flow in this way. Now this is N side, this is P side. So this diode, this is D1, D2, D3, D4. Okay. So this D1 will conduct, and the current here D2 will not conduct, current will come this way and flow through the RL in this direction. So then come in this direction and return. So you will get voltage in the RL. Now in the second half cycle, now this side is positive and this side is negative. Now the current will flow in this way D3 will not conduct, D2 will conduct, then current will flow RL in the same direction, then through D4, it will return to the transformer. So again, the current voltage drop across the RL always in same direction. Okay. So during first half cycle, D1 and D3 conducts, and during second half cycle, D2 and D4 conducts. Okay. So in this way, this bridge circuit can be used as a full wave rectifier, and here we are using the whole transformer. Here we are using the whole transformer. Now, as you can see, the output is direct, but it is not smooth. To make the output smooth, we need to use some kind of filter circuit. So what is the purpose of the filter circuit? The output obtained from a junction diode rectifier is unidirectional but pulsating. The output obtained from a junction diode rectifier is unidirectional but pulsating. Such a signal can be considered as a sum of AC and DC signal. So it is basically superposition of DC AC signal with the DC signal. To make it smooth, we need to separate the AC component from the DC. Now, filter is a device which used for separating the AC component from the DC. Filter circuit is the device used for this purpose. There are different type of filters out there. Some called series inductor or L type filter, only inductor type filter. There are capacitor filter. Just the output, before the output, we will use one inductor. Now, you know, inductor pass DC, but blocks AC. This is one inductor L. Here you have a load resistance R, RL. So here we will get the output. This is inductor filter. The reactance to AC is What is the reactance of inductor? 2 pi FL. So as the frequency is high, resistance will be high. For DC, the resistance is 0. So DC will go comfortably through this inductor, but the AC will be blocked. Then we have capacitor filter. So here the capacitor is used in series because capacitor passes AC but block DC completely. The resistance of the capacitor to DC is infinity. So here we will use one capacitor. The AC component will pass through this capacitor and only the DC component reaches to the output RL. So the AC will pass through this capacitor, which is connected in parallel, and that only the DC component will be received as the output end. There are another different type of filters are used, other which is called pi type, where two capacitors and one inductor are used. This is pi type filter. L type, where one inductor and one capacitor are used. So there are different types of filters which can be used to smoothen the output. To smoothen the output. Now, as I mentioned, when the diode is connected in reverse bias, there is a breakdown at certain voltage, which is called Zener breakdown. This process occurs in heavily doped junction diode. So due to this higher dopant density, the depletion region is very narrow. So depletion region is very narrow due to the higher dopant density. Very narrow due to higher dopant density. That means here there is quite high density of holes present at the p site and quite high density of electrons are present at the inside. So depletion region will be very small. Now, so when the depletion region is very small, depletion field is very high, barrier field. Because E is equals to V by G. D is the width of the depletion region. V is the barrier potential. So as D is very small, this barrier field is very high. So when large reverse bias is applied across such a diode, the depletion region and the energy bands get modified, and the energy So what is happening due to modification of the energy band? This is the conduction band. This is the valence band. Now here, say this is the conduction band. And this is the valence band. So the electron from this side will go to the conduction band of the other side. Electron from the valence band are not going to this conduction band, but then directly go to the conduction band of the other side. Similarly, holes from this side will, holes from this side will come to this side. So there is a huge increase of the current due to this. And you will get a breakdown. This is Jenner breakdown. Another breakdown, as I mentioned, avalanche breakdown. The process occurs in diodes having low level of doping and hence wide depletion layer. When the reverse bias voltage is sufficiently high, the minority charge carrier get highly accelerated. Then kinetic energy becomes very high enough, and they just breaks the bonds. This is Zener breakdown. Another breakdown is avalanche breakdown. So in Zener breakdown, what is happening? The minority carriers are going to the opposite sides where it will become majority carriers. So due to huge flow of minority carriers across the junction, there is a breakdown. It is called Zener breakdown. But in Zener breakdown, there is no breaking of bonds. But in avalanche breakdown, when the reverse bias voltage is very high, minority carriers are highly accelerated. So they have high energy, collide with bound carriers, breaking of bond, large number of carriers are generated. So you will get huge current. So this is avalanche. Okay. Now, this Zener breakdown has been used to prepare a special kind of device which is called Zener diode. And it is a junction diode specially designed to operate only in the reverse breakdown region. Continuously. Without getting damage. Now, in reverse breakdown, what is happening? The reverse bias resistance is very high. So when a large current is flowing, there is a huge amount of heat generation, I square R. So the diode may get burned. It is happened in case of avalanche breakdown, but also it may happen in case of Zener breakdown if it is not specially designed. But we have designed a special type of diodes which is operated in the reverse breakdown region continuously without getting damaged. This type of diodes are called Zener diode. We can have Zener diode with different breakdown voltage are available. The circuit symbol of Zener diode is a little bit different from that of the ordinary PN junction. It is used as voltage regulator. Because the voltage across the Zener diode remains almost constant in breakdown region, as voltage across the Zener diode remains almost constant in breakdown region. Does not depends on current. Now how it is working, I'm just showing you. This is called RS, safety resistance. Here and Zener diode having voltage drop Vz, and here you have load resistance. In the output, you will get the voltage drop Vz because they are in parallel. And this Vz will always remain constant. When current increases, Iz increases. So current width through the load will remain same. So the voltage drop across the load will remain same. The extra current will pass through the Zener diode. So the output voltage will remain equal. V output will equal as Vz. Okay. So the DC current from the rectifier is coming. Now we need the output at the output a constant voltage. So what we will do, we will use a Zener diode in parallel with the load resistance. So whatever may be the current in the circuit, the current to the RL will remain unchanged. It is always give you the voltage drop which is equals to Vz. The extra current will pass through this Zener diode. Is it understandable? So if we plot the input voltage versus the output voltage, both are in volts. So initially it will go up to Vz. Then the output will remain constant. So this is a special type of device which is used for voltage regulation, and it is called Zener diode. Now, as I mentioned earlier, that photons, that means light, can control the flow of current in a semiconductor diode. This property has also used to prepare a number of photoelectronic devices. These are called special type of devices. The PN junction can be designed so that the current through them changes either by casting electron, causing electron excitation from valence band to conduction band by light photons, or conversely through electron excitation by a switchable bias voltage, resulting in emission of light photons. So what we can do, the PN junction can be designed so that current through them changes either by causing electron excitation from by electron excitation by light photons, electron excitation means exciting electron from valence band to conduction band, or conversely through electron excitation by switchable bias voltage resulting in the emission of light photon. That is the light emitting diodes. So these semiconducting devices are called optoelectronic devices. Or photoelectronic devices or photonic devices. So there are two types of photonic devices. In one, where the current is controlled by uh, light photons, by casting light on them, okay, by incidence of light on the diodes at the junction, we can change the current. This is one type of device. Another type of device, by exciting the electrons with some suitable bias voltage, we can have emission of light photons from the diodes. Okay. So the photonic devices are classified as photodetector, photovoltaic device, and device for converting electrical energy to light, which is light emitting diodes or diode laser. One is photodetectors, which is used for detecting light signals. Examples: photodiodes, photoconducting cells. The light meters use this type of device. Secondly, photovoltaic devices. Which converts light energy into electricity. Example: solar cell. And third, devices for converting electrical energy into light. Example: light emitting diode, LED. And diode lasers. So mainly 3 types of photonic devices are available. Just a minute. Hello. I'm not getting details discussion of these special devices. So this is all for these semiconductors portion. I'm sending you a few problems. Do them. Just giving you if you have interest, you can go through these portions in your book. If you find any difficulties, you can discuss with me. But for your exam purpose, these are not very much important. Okay. They are not basically
Not
under
regarding
the
any exam.
no. They are not basically inside the syllabus. If you have some interest, you can go through it. I think you can understand. If you find any difficulties in understanding, you can call, you can discuss with me, no problem. And before joint, even in joint changes, these portions is not very good. I am sending you 4 problems. Please go through them. Let's do this problem.
Turn number 12 is done. So,
Are you doing? Shomallo?
turn number 12 is done. And
Just a minute.
13 the
Just a minute.
odd.
Yeah. What are you saying? Yes.
12 I have done, and 13 for the forward bias I have done. I have did that forward bias. 13
12 you have done. What is the
reverse
result?
bias.
What is the result in 12?
For 12 results. Yeah.
For forward bias and reverse
Coming
bias.
8. Forward bias is coming 20 ohm,
Yeah.
and for reverse it's coming 8 into 10 to the power 6 ohm.
Okay. Now you are doing the 13th
8
one.
into 10 to the power 6 ohm.
This is for 13.
Yeah.
And for forward bias?
For forward bias at 2 plus. For the number 13 at 2 plus, at plus 2 volts it came 20,
Mm-hmm.
and for at plus 1 volt
Mm-hmm.
it came plus 1 volt 20. Oh, sorry, for plus 1 volt is 40, and for plus 2 volt is 20.
Okay. Now 15, 16, have you done? 15th one?
15 also I have done.
Mm-hmm.
15th, the voltage drop is 2.3, and
Okay.
the wattage is coming 4.6 into 10 to the power minus 2.
Okay.
And
What?
so is the wattage of the diode, wattage yeah wattage of the diode is came 1.4 into 10 to the power minus 2.
Okay. 16th. 16th.
16 I have not done.
Okay. Do that 16th problem.
Yes, 16 I have not done.
Are you unable to do that?
Yes.
Or you haven't tried yet?
16
Have you tried?
I have read the question. I'm a bit confused.
See, from the figure, okay, when the positive terminal of the battery is connected to point A, okay, when the positive terminal is connected to point A, then the upper diode, which is connected with 10 ohm, that will become active, and the lower diode, which is connected with 20 ohm, that will become inactive. So current will be 2 volt by 10 ohm. In the second case, when B terminal is positive, then the lower diode will be active, but the upper will be inactive. So here the current will be 2 volt by 20 ohm. Okay.
Yeah. Okay.
So
Yeah.
just find which diode is active in which region. Okay. So I am just switching off for 5 minutes. Then we will join again. Okay. Thank you.